Dear all, welcome to this new episode of the CATIA TV, this time focusing on MBSE, Model-Based Systems Engineering, on the merge of systems engineering with Magic Grid and the ModSim approach. So to make an explanation, CATIA is a global leading expert in model-based system engineering with the acronym of MBSE, which can be defined as the formalized application of modeling to support system requirements, design, analysis, verification, and validation activities beginning in the conceptual design phase and continuing throughout development and later lifecycle phases. So in this CATIA TV episode, you will discover a strategic presentation of the latest innovations of CATIA on model-based system engineering. You will learn how CATIA uses the MBSE approach in product design and its functioning, coupled with the CATIA Magic solutions, precisely using CATIA Magic Cyber Systems Engineer, which corresponds to the legacy solution. You will also have the latest insights on how to use the 3D Experience platform for collaboration between systems engineers and product designers. So this webinar will be led and illustrated by very specific interventions and contents from our CATIA Systems Engineering subject matter experts, Gauthier Fanmuy, Rokas Bartkevicius, and Arnaud Durantin, who are the three of them are subject matter experts in the field of model-based systems engineering. This CATIA TV webinar will be posted and broadcasted on the CATIA community, so don't hesitate to interact with us, to ask your questions, and we will be able to answer you live on the post of the community. So thank you very much for watching this webinar, and have a very good day.
Industry is facing growing technological challenges. We are now in the world of cyber physical systems. It means systems that are software intensive, distributed, connected, that are interacting together. We're in the world of Internet of Things. What you see here is numbers of, I would say, components, interfaces, function of typical program. What will increase drastically in the world of cyber physical systems is mainly the number of interfaces and the number of interactions. And this leads to a stronger complexity. State-of-the-art practices of system engineering is mainly document-based in the industry. The drawback is that how can you ensure that all engineering documents are consistent together, how they are synchronized, how can you ensure that a given specification is consistent with a design, is consistent with a test, all of that with many updates at many levels, at many disciplines in the time frame. Also, many errors are introduced in the early phases of the development program, and so they are detected very late in the process. And so, how can we ensure that current state-of-the-art practices is suitable to this world of cyber physical systems? The response is obvious. We need to switch to a digital engineering with the extensive use of models in order to resonate, conceptualize the future system and simulate it. And companies are transforming themselves. And we speak here about the digital thread, where we can have a digital continuity, a digital twin from the early design down to the delivery of the system and the in-service. And model-based system engineering is one of the first elements of this digital thread. MBSE is simply the use of models for system engineering. So it allows to cover different activities of the engineering, such as requirements, system analysis, design, etc., etc. We speak here about defining a model. So it means objects that are reusable, where you can also simulate them, and not about, I would say, drawing pictures, which are not, I would say, system engineering reference. What you see here is a very short illustration of what is, I would say, document-based system engineering and what is model-based system engineering. Model-based system engineering really helps you to resonate on your system. What are the scenarios of your future system? What is the behavior of the system? And then, of course, what are the requirements of the system? And the system model is key. It's key because it helps you to define your targets, to define your scenarios, your missions. It helps you to define the interfaces between the components. It helps you to define the behavior of the interfaces dynamically so that you can drive, I would say, the design of the product with all the disciplines. So it means that you can specify. So from the system model, you can define system requirements so that you can specify the different components and the different behaviors that the components will have. Also, it helps you through, I would say, some simulation to make some system analysis. So to simulate the behavior of the product very early in the conceptual phase where you don't have any product. And also later on, when you have some first virtual component, to simulate progressively to achieve some integration, verification, validation, and to ensure that you all meet the targets defined early in the program. Of course, this needs to involve all the ecosystem, all the value network. So it's about collaboration between disciplines, but also between the suppliers and the OEMs. To achieve MBSE, you need best practices. So it means defining proper system engineering methodology, supported by some tools. And we have developed in Dassault Systèmes a methodology called Magic Grid, which is applied to the Cameo system modeler, and now extended to the overall development with CyberMagic Grid. The principle is simple. You define a framework so that you can manage different layers of abstraction, and for each layer of abstraction, you define different pillars, different point of views, so that you can see your system against these different point of views. So it helps you to ensure a complete and consistent, I would say, analysis and definition of your system. The benefits of MBSE is really to master complexity, master interfaces, considering both the static and dynamic aspects. Also, if you have a proper best practices in a modeling and simulation approach, it helps you to manage uncertainties all along the development process. So that with the simulation, you can take, I would say, front-load decision so that you can mitigate the risk very early in the development process and avoid, I would say, reworks, redesign lately in the development. Also, with proper end-to-end traceability, you can really master, I would say, the impact of a change, considering both a change on the needs, but also a change on the implementation or the design of the product. And also, it helps you to globally to reduce your rework loops so that you can be more efficient and develop a product right for the first time.
Hi, I'm Rokas from CATIA NoMagic, and today I will give you a demo of one of the best SysML modeling tool in the market, which under the CATIA Magic portfolio has a name, CATIA Cyber Systems Engineer. So in today's demo, I will show you Magic Cyber Systems Engineer together combined with Magic Model Analyst. So for Magic Cyber Systems Engineer, we will be creating the system's functional and structural architecture, and using Magic Model Analyst, we will do the model execution. So in other words, so there is a code-free model simulation, validation, and requirement verification, which you can do in early stages of product or system development lifecycle. For our demo, I have chosen the advanced emergency braking system as a context, and the system which can automatically detect the potential forward collision, and of course activate the vehicle braking system, so to decelerate the vehicle in order to avoid or mitigate the collision. So for presentation, so we will be using the Magic Grid, which is model-based systems engineering modeling framework, and the Magic Grid has the main 4 pillars. So there is a requirements, behavior, structure, and parameters, and then there are the different domains. So the purpose of the problem domain, which you can see there is a black box and white box, is to analyze the stakeholder needs, refine them with SysML model elements, in order to be clear and coherent, to have a coherent description of what problems the system of interest must solve. And as we have 2 focuses, so 2 perspectives, so there is a black box and white box. So the black box is focusing mostly on in order to get or acquire knowledge about the environment, without any details in internal structure behavior. And we can call that like operational analysis, and the functional analysis, so the white box, is looking to the detail, so helps us to understand in detail how the system should operate. So, and then there is a solution part. So the solution part, in solution part, we have an architecture. There is a functional and logical architecture of the system of interest, along with the parametrics and of course the requirements in different scopes. As we can say, there is a system, subsystem, component. So it depends how deep and what kind of granularity you have in your context, and it helps you to define and to give the answer for the problem domain analysis model. So sometimes, there are the cases where a OM is working on a problem domain, and then we ask for suppliers to provide the solution, which means that you can get multiple solutions also, and to make the trade-off based on your requirements. Okay, so let's go a bit deeper in each of these parts. I will cover just very quickly because there are the separate webinars also focusing on the Magic Grid. In that demo, my focus is more to show our tool and to show the capabilities also of the simulation. So the stakeholder needs, which usually we are getting from the other requirements management systems, and we have a capability to import and also synchronize the requirements using the Cameo Data Hub plugin, and we can import synchronize requirements from IBM DORS, the both classical and also DORS NG. Also, there is possibility to import from the Enovia requirements manager. So the trigram is TRM. You can do that from Excel as well. And the requirements in SysML, so we have a specific element. There's a requirement element, also the text, and as you can see, so there are also the images imported, and we can have the other columns like in the table format, where you can display another elements connected to the requirements, refined, buy some elements, derived requirements in lower level, etc. So then we have the from the structural part. So we have a system context. The system context when you talk about your system of interest and environment with that, how it interacts with environment, high-level picture of your system of interest, and identifying the main use cases. The main use cases which defines the main functionality of your system at very high level. Like in our case, there is assist braking. We have activate autonomous braking, including assist driver braking, etc. Then there is also the measurements of effectiveness, so which is actually some kind of a KPIs, and so where you capture the non-functional user goals, which are expressed in numerical format. And when we go to the white box, so into the details, so we have the logical architecture. So the architecture very high level, just identifying the main systems or subsystems of your system of interest, and the functional analysis. So in the functional analysis, you identify the functions, you can define also the behavior which you expect from a very high level. So as I mentioned, this operational analysis from operational analysis context, we can have also the some kind of a breakdown structure, like a functions breakdown structure, and then we go to the solution domain. In solution domain, of course, so there are requirements, the system level requirements, and there could be lower level requirements, a subsystem, etc. So which usually we are deriving from the upper level requirements. Like in this case, you can see that the requirements, system level requirements, they are derived from the stakeholder needs. And one of the example I will take the requirement CCR's compliance test, TTC, equal less or equal 10 seconds. So what does it mean here is that the car-to-car rear stationary, so the compliance test and when time to collision is less or equal 10 seconds, so it should show the warning mode. So and here we can see also which elements are satisfying that requirements, or even some kind of test cases which are verifying that requirements from a model. What is really nice that you can connect not only the elements but also some of the relationships. Like in this case, there is a transition which is used in the state machine to transition from one state to another state. And in the solution architecture, of course, there are more details. Here we are showing just example of that details, but when you have some system breakdown structure and you define the subsystems also, which will be providing the solution for your system of interest, and then in the system behavior context. In this example, so we have the state machine, which is defining all the possible states for the emergency braking and for that system. And actually, there are also defined what should happen if we are in the specific state. For example, like if we are in a warning state, so that there should be displayed the warning message, and there is still no braking. There shouldn't be force braking, but the force braking is when we are in the braking state. So, and in this case, I can just easily execute such state machine as a system engineer to identify if there are any problems, or let's say to verify my state machine and my business logic, which I defined as a system engineer. So then I running the state machine. So we are coming to the initial state, and we are at the moment is in unavailable state. So I need to manually send the signal to start my collision avoidance system initialize and that it would be available and also operational. And in that case, so we are in identification state. Just for the demo purpose, I have some checking all the time. So it's after 5 seconds, it's checking all the time what is the state. And we have a time to collision property also is equal 10. So we see that we cannot transit to another state to warning because it's equal 10, and here we have it time to collision is less than 10. What does it mean? So if you remember, so when I was showing the system level requirements, there was said that time to collision is less or equal 10. So what does it mean? The requirement probably was changed, but the model according to this state machine, so it's not changed. We have very nice functionality which calls the suspect links to double check. Let's see, the requirements were changed from the business level or from our colleagues. So how do I know that that's I need to consider something unless there is a communication? Or we can have a suspect links and to analyze the suspicions, which means that all the requirements which are connected with the other elements, so using like satisfy, refine, or other relationships. By way, you can also define manually what you want to track. They can check the changes, and if the change is made, for example, in our case in the requirement, then it shows the link as a suspicious. So in that case, so I can check my transition to just let's locate it in a diagram. Yeah, so that's transition, and let's see what are the changes, actually the changes in the requirement. And what's happening now, so it's checking from the server the changes, and it's showing that in the version was comparing to the last versions, and it's showing that actually the equal was added by some of our colleagues. So what does it mean? I need to work on this suspicious, and in that case, so in my logic, so I need to put the sign here and say that, okay, I'm clearing that suspicion. So now is correct. My state machine is correct, corresponding to the requirement with which I have connected that specific transition. So let's see how we can model the user interface in terms of the simulation. So in that case, we can use the user interface mockup. So we have a specific diagram where you can just put the layout and add the buttons, images, etc. And what is really nice that each button or the specific elements of the user interface, so we can be connected directly with the model elements. Like in that case, the signal start, when you click the button, so it's sending to the system the signal start. What does it mean for us? It means that we will send to the state machine that signal. Okay, so let's see our state machine, and let's see our dashboard. So if I click the signal start, as you can see in the state machine, it's waiting for a signal, and when I click signal start, it got that signal in a state machine and changed the state. And we can see that it is correct based on the requirement already, that the warning is displayed. Yeah. If I, for example, if I can reduce the time to collision, for example, to 2 seconds, and let's see what happens then. So there is a full auto brake, so which means that we are getting in the state braking. And in such case, so you can prepare the user interfaces, for presenting to your management, to your colleagues, also the specific problem or specific solution. Okay, so let me stop this simulation, and as we are talking about the emergency braking system, so then collision avoidance, we should not forget so which system does the last job, so which is a braking system. Yeah, and let's see how we can analyze the the stopping distance in such case using the SysML parametrics diagram. In that case, I have the in my structure, so there is specific parameters defined. So we call in value properties in SysML, and there are like a gross weight, stopping distance, so which we need to calculate also parameters, and also the entire structure of the brake, also including the pad caliper with its own properties. And as there are the requirements which are saying that 4 braking wheels shall be capable of stopping vehicle from 100 kilometers per hour in less than 59 meters. So we need to consider that requirement and see how we can calculate that. For that purpose, we are using the parametrics diagram, SysML parametrics diagram, which gives you capability to define the calculations. And here, as you can see, so there is a stop distance calculation, so the formula, which is using the input values like a gross weight, like a speed, and others, in order to calculate the stopping distance. After stopping distance is calculated, it is sent to another constraint, and we have another calculation where we compare the stopping distance with required distance in order to have the final verdict. Is it passed or failed the specific configuration? So as the requirements are, I was showing already these requirements, just the table format, as you can see, so we can play around with the different views. So you can see requirement also in the diagram. You can display them in the tables, and you can also show the different columns to display additional information, additional metadata also. And here we see that the stopping distance is satisfied, this requirement is satisfied by the property stopping distance, and is also refined by specific constraint and from the functionality point of view, so the activity apply brakes. And for that purpose, so in order to display the functionality using the simulation and also bringing some nice widgets. So we have a cost-free plugin which is capable to run the JavaScript HTML widgets. So we call that Web Server for Cameo Simulation Toolkit. And I will show you how easily you can add additional widget in order to display value of a specific property. So we have some predefined widgets library, and I'm taking one widget, connecting that with the property which I want to display, and then hiding that property. Yeah? Hiding that connection, and of course I need to give a name of my widget, so it will be required distance, and also I will hide the type. That's all. So I'm ready to run my dashboard and analyze the car brakes. Do the car brake analysis. So let me bring the simulation tab on the right side because it's easier to analyze here. And as you can see, the stopping distance requirement is failing. And here we can see that the stopping distance, current stopping distance with current functionality is 62 meters, more than 62 meters, required is 58. So I can manually adjust the tires diameter to see, now is a green color, to see that if it's passing or not. Let's say I want to have a 21, then maybe I need to reduce the weight. So if I'm reducing the weight, then I'm satisfying that requirement. And in such case, so you can, as a system engineer, you can work and analyze the requirements, and also to figure out which combination should be for your car, for your tires, etc., in order to satisfy the requirements. The other way is that you can have the multiple configurations, and actually these configurations, so they can be failing some specific parameters, etc. And we can calculate that using the same parametrics diagram. Let's say that I need to increase these numbers, and I can re-evaluate. So I do re-evaluation for each of the column, and what we see is that we failing. Two combinations are failing as a final result. And I can also work with the Excel spreadsheet, which means that I can save my configuration to the Excel spreadsheet, send to my colleagues, which can work forward and bring another configuration. So let me just export that Excel spreadsheet, and I say that okay, so we will reduce the weight, and we will reduce the wheel diameter, and saving that Excel and read from file. So reading from file, we are getting the values which were in a file, and then we can re-evaluate again. So before that, just let's remove the Excel import status legend and re-evaluate, and we see that actually all the configurations are passing for the stopping distance, but just the problem is with the gross weight. So at last, I want to focus on the traceability part, and as you know that I was showing already with some requirements, so which are traceable with your logical and functional architecture. And the other thing is that this traceability is actually for the systems engineers, and in order to trace all the model elements. And if you want to have a full-scale traceability, so at enterprise level, this full-scale traceability can be achieved using the 3DEXPERIENCE platform, the traceability between different roles and disciplines also. And here I'm finishing my demo and giving over the stage to my colleague, who will show you the full-scale traceability in 3DEXPERIENCE platform. Thank you.
Hello, I will introduce you how to manage collaboration within the 3DEXPERIENCE platform using the roles Systems Traceability Engineer and Systems Traceability Analyst. Those two roles provide an app that you can see here that is available as a widget of the 3DEXPERIENCE platform. There are three pillars of collaboration: sharing data, traceability analysis, and reviews. And I will introduce you how to manage those three pillars using this application. First pillar, sharing data. So systems traceability enables you to preview models based on connectors to a various set of solutions, like Cameo, Simulink, Microsoft Office, or other solutions like IBM Rational Doors or Rhapsody or whatever. We have more than 30 connectors available as of today, and the list is increasing release after release. So here, as there is an example, I can navigate through a Cameo model. Here this is a Cameo model that was presented to you just before by Rokas, and I can navigate through it as if I have a Cameo solution. And I can select the object and access to its properties, as you can see here. I can also navigate through the data like this, and it selects the data. I have also a connector to to some object authored within the 3D Experience platform. Here it's a logical architecture authored using our functional and logical editor. And I can also access to the data available from this solution. As you can see here, I can read a schematic. Here it's an electrical schematic or a Simulink model. And access also to the properties. C code coming from AutoSAR Builder. For the 3D object, here I can read the product structure, but if I want to see the 3D, I advise you to use the power of the collaboration between widgets, and you can load the data to a widget called 3D Play that is available within the 3D Experience platform and that supports the analyzing of the 3D. So as you can see here, you can use the power of the 3D Play. You can filter the data. And for example, here we are talking about ABS. I can see the 3D design of the brake. You see? I can have a look at it more into detail. Second pillar of the collaboration is the traceability. So still based on the connectors of various set of heterogeneous model, this solution enables you to create and analyze the traceability between those solutions. So as you can see here, systems traceability use the concept of a scope of data. Here I created a scope of data using a subset of a Cameo model here, a subset of a logical architecture here, and a subset of the discipline detailed design. And the arrows, the gray arrows between those models elements are called channel. The gray arrows between those elements are called channel, and the channel supports the traceability analysis. So I'll show you. Here I have an indicator that tells me that I have some work to do, and by double-clicking on the bubble, I can see the traceability between elements. And if I select an element, I can navigate and analyze the traceability. Okay? It's possible to view the full traceability upon the scope that I presented to you just before. So if I click on impact analysis, as you can see, I can navigate through the full traceability, and I can, here for example, this requirement, I can analyze the full impact of a change to this requirement. Okay. So if you prefer, you can create some tables to support this analysis. And I created several tables based on the data available on the scope. So as you can see, sometimes it's not very clear to read those data. And we can use the power of the 3D Experience platform to support you in this analysis. So for example, here, if I select an object, I can see the object in its context. Okay. Okay. So very powerful solution, and you can analyze the traceability and share the data. You can also analyze your model using analysis scripts that you can edit that we call semantic browser. As an example here, I can analyze the scope to identify the objects that do not have incoming link. I call this script the uncovered object, and here I selected the scope AEBS, and you can see that I have the full list of all the objects that are supposed to have a traceability and do not have traceability for now. So the object, I have to work on it. This list I can export it to Excel or just preview the object. Okay, this is the object that is supposed to have a link, this one, and so on. Okay. Third pillar of the collaboration is the review. Today, if you want to make a review, you do it in 2 times. First, you generate a document that you share with an Excel sheet for comments. Then, you organize a meeting with your colleague to review the comments by reading the Excel and searching in your model or the document you generated, the commented object. Upon the preview and traceability solution, it enables you to directly annotate your model and share those annotations with your colleague. So it can support the review process. So here, as an example, I have a task, make models review, where this task is assigned to me and I can assign it to other people. And in attachment, I have the documents to review and the deliverables. Based on this, I can load the data to review and enter in edit mode for the review. Oops. If I navigate through the models, so let's go down again into system behavior, you can see that some comments already exist. I can answer to it. Or I can add new comments. You can put comments on any object available and read by the 3D Experience platform. Here is comments on a Simulink model. Or you can put comments here. I will put comments on the logical architecture. Those comments exist already. And at the end, once you've shared your comments, you can read all the comments in a table. Okay. Then, what you can do is you use the power of the 3D Experience platform to read the comments and see them directly in the context of the model. Based on that, you can take decision. So for example here, this comments is about we need an hysteresis around 10, okay, between those two objects, those two states, and someone else agreed to modify So I can close the discussion by saying that the hysteresis shall be added. So, as a takeaway, this solution is a federation solution. It, with all the connectors, it breaks the silos between disciplines. It ensures the end-to-end traceability in heterogeneous environment. It provides visibility of relevant engineering data for better project control. And it eases and accelerates convergence between teams in the value stream. So for the collaboration, we notice that it can provide you a productivity gain of more than 40%. Thank you very much for your attention.